So let's talk a little bit about solubility. We've been talking about solutions for a while now. So solution is something where we have a solute that dissolves in a solid. So solubility looks at that in a quantitative sense, and that is the measure of the amount of solute that will dissolve in a given volume of solvent. To give a couple of examples, let's take a look at magnesium sulfate. This is considered a fairly soluble compound in water. Basically, you can dissolve up to about 35 grams of it in a 100 milliliter aqueous solution at room temperature. However, on the other hand, cobalt hydroxide is an extremely low solubility compound with a solubility of basically 30 thousandths of 1 gram per 100 milliliter of solution. We could call this functionally insoluble practically. So why is it that different solutions have different levels of solubility or are incapable of being formed because that the solute, would-be solute, is basically insoluble in water? The complexities of the actual molecular attractions are a little bit more complex than we want to get on in this video, but there are a series of trends that can help you predict whether a solution is likely to be formed in an aqueous solution based on some basic trends that we have. For example, nitrates are pretty much the only type of solutions that almost any metal will form into a solution. So that means that even the really insoluble metals like lead and silver will form a solution with them, and almost nothing else, when nothing else will. So most metals will form very soluble compounds with nitrates. So these wind up being among the most soluble of all aqueous ionic solutions, with a metal cation and a nitrate anion. Also highly soluble are solutions where the solute has a cation that is an alkali metal, like lithium, sodium, potassium, cesium, rubidium. They tend to form very, very soluble compounds. Also, the halides, -1, chloride, bromine, and iodides also tend to form pretty soluble compounds, except with some of those really heavy metals like lead, silver, and mercury. Then we get into moderate solubility solutions that are based around the polyatomic ion sulfate. Sulfates tend to produce fairly soluble compounds, although there are some tough metals. Once again, lead and silver sulfates are not soluble. Calcium sulfate extremely low on the silver insoluble, strontium sulfate as well. Hydroxides tend to not be very soluble for most compounds. There are a few that have a decent solubility, but most are either have a low solubility or are just completely insoluble, particularly if it involves a transition metal with a hydroxide. Carbonates are often insoluble at all or have a very low solubility, like calcium carbonate. You can dissolve a little bit of water, slightly soluble, but for most metals, combining with a carbonate is going to produce an insoluble compound, and thus you just won't get a solution in water. Phosphates are generally insoluble. Pretty much the only soluble phosphate compounds tend to be with alkali metals. Not particularly high, but you can form some solutions, say sodium phosphate or potassium phosphate. Outside of that, almost any other phosphate compound just won't dissolve in water to any meaningful degree. And then, as you have probably noticed on these other trends, lead and silver tend to be insoluble in almost all compounds except in their nitrate form. And so, as a result, pretty much the only way we can get an aqueous solution with these two metals is if they are in a nitrate form. So, what we're going to do is we're going to take a look at a few compounds and see if we can predict their solubility. We have 6 compounds that we're going to look at and see if we can predict fairly accurately if they will be soluble in water, slightly soluble as in fairly low solubility, or insoluble. So our 6 are sodium nitrate, A, silver sulfate, B, manganese 2 chloride, C, iron 3 hydroxide, D, potassium phosphate, E, and calcium phosphate, F. So take a look at the solubility trends and see if you can predict whether you will have a soluble, slightly or low soluble compound or an insoluble compound. Pause the video and take a minute to make your predictions and then start it up again and let's see how you did. So, I've listed the table of solubilities at room temperature 20-25 degrees of our solute in mass per 100 milliliters of solution that we presume is going to be almost all water. So sodium nitrate, not surprisingly, is extremely soluble in water for 2 factors. It has a cation that is an alkali metal, which usually produces very soluble compounds, and nitrate, which is probably the anion, common anion that produces the most high of all solubility of aqueous solutions. Then we look at silver sulfate. As we can see, it's pretty low solubility, almost insoluble, really. We have less than a gram per 100 milliliters. This is because silver is a notoriously insoluble metal and is being dissolved in sulfates, which tend to produce only moderately soluble solutions. So whereas the silver being bonded or to sulfate when it is in its dry anhydrous form does keep it from being 100% insoluble, we can practically almost call this insoluble. Manganese chloride, or manganese 2 chloride, is pretty highly soluble in water. Transition metals like manganese kind of vary in their solubility, but the fact that it is combined with an anion that is a halide, that really raises its solubility potential. And as you can see, this is a pretty high solubility compound. Iron hydroxide. This fits the classic pattern of a hydroxide with a transition metal, and it is, for all intents and purposes, insoluble under normal conditions, room temperature, normal pressure, neutral pH water. We would have to acidify this water significantly to get the iron to dissolve. Potassium phosphate. So here we're combining a very soluble cation with a frequently insoluble anion. And we do get a pretty soluble compound. And alkali metals create pretty much the only high soluble phosphate compounds that there are. But contrast that with what happens when we take a phosphate and combine it with some other cation, like calcium. In this case, the solubility is essentially insoluble. Basically 0.002 grams per 100 milliliters or 2 milligrams per 100 milliliters. We can pretty much call that insoluble. So hopefully you'll get used to these trends as you continue in your lab practice and notice that there's certain tendencies that you'll see. Nitrate compounds tend to have a very high solubility rating, as do chlorides and alkali metals. But once we get into things with really heavy metals like lead and silver and phosphate and hydroxide and carbonate compounds, the solubility drops down dramatically.